Welcome to this second video in the series on regression, multiple regression on Excel. This is Dr. Stephen Haird at the University of Dayton, and thank you for joining me. Let's get started. Welcome. We're going to take a look at the residuals, the estimated regression function, the Anova table, the t-test calculation, and the confidence intervals based on the t-test statistic for a multiple regression. A multiple regression is one in which there are multiple independent variables, multiple x's, and multiple parameters, beta parameters, for those independent data points. Here's a sample data set. This is visualized as a record of salary figures for employees. The salaries are the dependent data, the Y data values, and the two columns on the left, the experience and the test, are the independent values, the X values. Experience might be, for example, years of employment experience, and test might be some kind of employment assessment test, some kind of exam. And so we're trying to see what is the relationship between experience and testing for this salary. Let's go ahead and pull this data out and put it into the spreadsheet and see what happens. So here is our data right here. And we're going to use the data tab here and the data analysis tool, regression, right there. And we need to select our data. So let's first of all, let's select salary. Now notice this is the dependent variable, the Y variable, and I have the labels box checked, and I have selected the label at the top of the column with my data. What that does is it means now Excel will use that information to label the results when we see the result here soon. I don't have to do that. I could turn this off and not do that and just select the data alone without the label. But then my data has a very generic set of labels and I can't see that label when I do the solution. So I am going to select the label column and do like this. Here we go. Same thing for the X data. Let's get that cleared up. So I want this. Here's my X data. So I need to select it together. The data needs to be together in two close columns like this in order for this to work properly. And again, I've selected the labels at the top of the columns. I've got the residuals box checked. I have the residual plots box checked, and I have the standardized residuals checked. I'm going to get those residuals and take a look at them. So we're ready to go. This dialog is ready to go. And here we go. Here's the solution. So here's our solution right here. Let's take a look at the residuals first. Here's our residual plots. These residual plots are the difference between the original Y values and the Y values that match on the fitted line that we just calculated with this regression. If I go down here below, here are the residuals in those plots. And then over here on the right is something called the standardized residuals. This is the residuals scaled so that they are scaled to the dimensions of a normal distribution with a mean of 0 and a standard deviation of 1. And this can be used to check to see how the distribution of those residuals looks in terms of how extreme they are. So let's take a look at the results on our slide set here. So we've got the regression solution here. We have the coefficient of determination, the correlation coefficient, the standard error of the estimate, and the something new right now, the adjusted multiple coefficient of determination. What is this? I'm not going to go into technical detail, but when you have multiple independent variables in your regression, you need to adjust the coefficient of determination. You actually make it a little bit weaker because, and I won't go into the technical description, but the bottom line is the more independent variables you have, the more conservative you need to be in terms of the claims you make about the fit of the line. And so this adjusted R-square, this adjusted multiple coefficient of determination is going to be a little bit lower than your original coefficient of determination to reflect this extra safety factor, this extra more conservative factor in the regression. So here's our fitted line. We have the intercept, the beta 0 here. We have the beta 1, which is going to be experience. That's our first x variable. Then we have our standard error of beta 1. We have our t-test statistics for all three in this column, all three independent values. And we have our t-test p-values for each independent value here as well. And notice that the intercept has a very large p-value. The intercept is not judged significant based on this information. We have the coefficient for the beta 2 for the test independent variable and the related standard error of beta 2. Over on the Anova table, we have our sum squared of regression, we have our sum squared of error, we have our sum square total, we have our mean square of regression, our mean square of error, and our f-test statistic. And right next to that, we have the f-test p-value. There are confidence intervals provided for us by Microsoft Excel. Notice that the left and the right sets of values are identical. That's normal, and you should expect them to be identical unless you go back to that original data analysis dialog and make some further adjustments. But in most cases, the default setting, these two are identical to each other. So these are the confidence intervals, the 95% confidence interval of what we think the true value of these parameters is. And you can see at the top there, the intercept ranges from -9 to +16. So it covers 0, which means we think 0 could be in the range, and therefore the intercept of that slope, that fitted line, is not significant. So let's take a look at another scenario. Sometimes we have data in which is not numerical, but which is a text category. It's a label. We can do regression on this data, but we need to convert that text into a number value. We do this and call it a dummy variable. It's either true or false, and we have one variable for each possible true combination in our data set. Let's take a look at this in our spreadsheet. Here's our data, and you can see we've added a third. This is the same data we just used a minute ago, but now we've added a third measure, whether or not these folks have a diploma, an educational degree. Some of them do, some of them do not. But we need to convert this information to a number before the spreadsheet can use it. So let me show you how we're going to do that. Here's our data. I want to convert this to a number. Now I could manually go through this and type the number in. That's certainly an option. It's very labor intensive. Let's try something else. Let's sort this data by this degree column. Select the whole thing. It's important. Not just the one column. You need to select the whole thing. And then let's sort it. Let's sort it by degree. I've already got that selected. I was doing this earlier, so it's already selected. By degree. And OK. And now it's sorted. And now let's go over here and put in some numbers. So now I have these numbers over here, and I'm just going to copy and paste those numbers over top this text. And now I can just get rid of this, and now I'm ready to go. Here's my data. I do not need to return this back to the original sort order. That's not necessary. It does not change the regression if I resort the data. The regression is not dependent on the sort order of this data. All right, so here we go. Data analysis, regression, and now we need to change some things here. So my Y column is now right here, and my X is now 3 columns, 1, 2, 3, like that, and everything else stays the same. I have my labels box checked, I have my residuals checked, and let's go. Let's see it happen. And there's the result. Now, I'm not going to walk through this in the slides because everything is really the same. The number values have changed, but what these things mean is identical to the slides that I just finished going over with you. We just have added one additional row. We've just added some more information here, and the degrees of freedom has increased. We now have 3 degrees of freedom for the regression. But everything else looks the same. Here's our residuals for the dummy variable, for the 0, 1, true, false variable, And of course, the residuals are concentrated only on 0 or 1 because those are the only two possible values for this dummy variable. Well, thank you. I've enjoyed presenting this to you, and I appreciate your time, and we'll talk again. Thank you very much.